With no further ado, it's my great pleasure to welcome Joost van der Weijer.
That's okay.
Sorry. Who is currently working senior VC at our laboratory. We have great pleasure of working together with, and Bartek is also affiliated there. So it's a great pleasure to have you here. Joost got his PhD from University of Amsterdam in 2005. And he was a fellow, Weijer at the Weijer team. And then he was another fellow, and Ramonia Cajal and de Barcelona. And apparently he fell in love with Barcelona, from what I heard. He didn't want to move back to the Netherlands. He serves frequently as area chair in major computer vision machine learning conferences. He's specialized in active learning, continual learning, transfer learning, a lot of learning things. And recently I found out that he started to read Sienkiewicz book that he tried to get ready for his So far it's Joost 0, Sienkiewicz 1, so it's not even 5, but we are figuring out. Thank you again for being here. And let's hear your talk. Thank you.
Okay. Thank you, Thomas, for the introduction. It's a pleasure to be here. I will talk today about towards label efficient and multi-agent continual learning. Most of the talk will be actually on the label efficient, and I will show some recent ideas we have on moving around forward from one single agent, which does the. I think this will be an interesting topic in the future where multiple agents are interacting. See if it works. This was awesome. Stop sharing a second. Okay. Magic touch. Yeah, it worked. Sorry about that. So, continual learning, I think for most of the people here in the audience, it's well known. We had a workshop at the Taagstoel a couple of months ago already, and we tried to define what it was. So we came up with the definition in the bottom. Continual learning is the learning from a non-stationary stream of data with the aim of accumulation of knowledge. And the non-stationary part was debated, and so there was no agreement on that part. Even it could be stationary. But okay, we have a stream of data. I think it's more the non-stationary part is kind of essential to your learning. It's changing over time. You want a learner is learning from this data, and you want to accumulate knowledge. So you don't want to forget previously acquired knowledge. So just quickly, some related field transfer learning. We all know about that. You train on a model on a large data set and you apply it to a small data set. In transfer learning, you don't care anymore about your source data set after adapting to the target data set. You just want to be good on the target data. In continual learning, you have a sequence of tasks. Here, for example, of learning dogs, then cats and birds. When you train a task, you don't have access to previous task data anymore, maybe some limited buffer. And at the end of it, you want to be able to perform all the tasks. So the main difference with, let's say, this transfer learning is that you don't want to forget previous knowledge. And the problem is that you will suffer what is called catastrophic forgetting. If you do this naively, you will just be good in the last task you have seen. If you would, for example, apply fine-tuning. Another field that we'll see a lot today, domain adaptation. And domain adaptation, the set of classes between the two domains, also often called source and target domain, remain the same. So example, a bed, bike, and a bottle, but the domain changes. So it could be real photographs to drawings of them. In domain adaptation, like with transfer learning, you don't care about your source domain performance after adaptation. You care about your target domain. Incremental domain adaptation is the following setup. You see these different domains, but in the end of all the domains, you still want to be able to recognize these objects in any of these domains. Again, catastrophic forgetting is the main problem. But continual learning has developed a whole set of problems here. It's an overview. I will shortly discuss two, just for the people who don't know. Replay-based methods is really the most efficient way to address forgetting. And you have a replay buffer here in the bottom with some examples from previous tasks. So in the buffer, we have now some examples from task 1 when we are learning task 2. And when we are learning task 3, we have some examples from task 1 and task 2. So you have, and these samples can be replayed while training the last task. This replaying will have the effect that you don't forget the previous task. So there is a whole set of methods around this idea. Regularization methods is the second important set of methods. Regularization loss is one important loss where you have the weights of your previously learned model and the current model, and you put some loss on it. You just want the difference between these two models not to become too big, and normally that's weighted, this loss. So you have a weight for each weight or parameter in your network, and which says how important this parameter was for previous tasks. If this parameter wasn't used for any task, then that's a good parameter to update in your network. Data regularization, also called functional regularization, puts the loss on the output of the network. So in this example here, the probabilities. And when seeing new data, you want the probabilities of the previously seen classes, maybe not present in the current data, but you want this probability to remain the same with your new network. And by using this regularization loss, you prevent forgetting. So one slide maybe on evaluation. So let's say the joint training with all the data of all the tasks is an upper bound for continual learning. Normally the lower bound could be fine-tuning, and continual learning methods, and typically in this example here on the right, are in between. So and the aim is to get as close as possible to joint training. And on this setting here, this is the cipher 100 in 10 tasks. You see that the gap is pretty big. So there is still, and these are even replay methods among these. So there is still quite some work to do to close this gap. Why would one do continual learning? Often this is a restriction from the setup. So there could be memory restrictions. Your device might have a limited memory, so you just cannot physically keep all the data you see, maybe in robotics. Might be privacy restrictions, so government legislation might not allow you to store the data for longer periods. And then the last point, maybe a sustainable artificial intelligence. So continual learning is an alternative to training from scratch. And training from scratch could be seen as a very inefficient way to train because you throw away all your previous knowledge. And this bottom point is now being started to be taught people in continual learning. So today I want to go into three directions actually, but the majority is on actually the first point. The vast majority of continual learning methods are supervised. So can we go to more label efficient methods, which are maybe unsupervised or partially supervised? We assume a closed world. So at evaluation time, we evaluate with the classes we have seen during training. So it can be moved towards an open world continual learning. And normally you consider a single learner, though there are some methods out there which use two learners. And I will also, so most of it will be actually on this first topic. I will do a little bit on this open world direction, more in domain adaptation action. And then the final one will be maybe some recent work we did in this multi-agent continual, or towards, I would more call it, not really yet multi-agent. So we were start with unsupervised domain adaptation, which is also a related field. So here they have two different domains. For example, you're training your algorithm on synthetic data and you want to apply it to real pictures. The main difference in this setting is that in the second domain, the real pictures here, the target domain, you don't have any labels. So in most of the continual learning methods, we have all the labels at every time. So here you don't have the labels in the second task. So there is a whole scala of existing methods there. I just wanted to mention one, which is maybe one of the most popular, which is the adversarial domain adaptation. Unsupervised. But here you have the two domains and you learn a backbone, which is in green. You learn a classifier on the label domain, and you learn one, let's say, adversarial network here. And this network, the aim is to classify between the source and target domain. And what you do is you do it adversarially, you do a gradient reversal, and you will make it impossible to do this task. And what does that mean? This means that the output features will be invariant for the two domains. And if they are invariant, the hope is that if you then on the target domain plug the classifier you learn on the source domain, this will also work. So this is one of the most famous unsupervised domain adaptation methods. But let's say here the problem is that when you train this, you really need access to both the source data and the target data. From, I think, maybe 2019 on, people started to go beyond this and say, yeah, this assumption that you actually have access to source data and target data in domain adaptation, maybe it's not true. Often you send a model to a device and you want it to adapt. And this new field emerged, which was called SourceFree domain adaptation, which in a sense very close to continual learning, where you also don't have access to your previous data. So here could be an example setup. You have a large cloud model and you set the model to devices. On the devices, you don't have access to all the training data on the cloud. So you have to now adapt to the user data on the device only based on the target data. So typical domain adaptation is this setting. You have the source data, the target data, and you test on the target domain. So again, you don't care about the source domain. In this source-free domain adaptation, you have source domain data, you do pre-training your network on it. Then this network goes to the adaptation phase where you only have access to target data. And then you still test on the target domain. So I made this diagram to show a little bit what are the characteristics of all the settings. So supervised. In continual learning, you don't have storage of previous task data. You normally have the labels for both the source and the target. So I put the red crosses there, and you care about all the performance. And then I would like to go to the situation where this is green, where we have all these characteristics. And now this source-free domain adaptation, it already has unsupervised target adaptation. So you don't need labels anymore when you go to the target domain. I wanted to discuss one method, which is the most popular method for source-free domain adaptation. And it's a very simple method. It's called SHOT. And they use two losses to adapt to the unsupervised domain. And very simple losses, the entropy loss and the diversity loss. The entropy loss just says that it's almost like wishful thinking, this method. It says that if my target model is good, it's sure about what it says. So I wanted to have a low entropy. I wanted the target model to say 0.001.0.0.0. I wanted to be sure. So that's this. You just, when you start with your source model on the target data, it will not be very sure. It will say 55% car, 45% bus. But now you start to push it, be sure, just be sure. And that's that loss. And the diversity says, I just want to see all the classes I've seen in the training. I want to see them in testing. This is maybe prior knowledge how academic sets are. This helps to prevent collapse towards a single class. But So this original method was still needing actually, no, but this was the first source-free domain adaptation method. So we wanted to go on from there, and we were looking at the features of the target data on the source model. And you see something like this. And you see that there is a clear structure. You see that classes in the target domain, this is probably a class in the target domain, still make nice clusters on this source model. So we wanted to somehow exploit this extra knowledge which you have, which was not used. So one of the ways to exploit the neighbor information could be to just impose a loss which says you should have the same prediction of your class as your neighbors. And that actually works very well. We went one step further. We started looking at reciprocal neighbors. Reciprocal neighbors are neighbors. A reciprocal neighbor is a neighbor for which you are also a nearest neighbor. So it goes in two directions. And if you look at the accuracy of the prediction of a reciprocal neighbor versus a normal neighbor is in blue here. Then you see that the reciprocal neighbors, which on the horizontal axis here, we have the number of neighbors we are looking at. In black, we see that the accuracy is significantly higher. So using the reciprocal neighbors is a stronger predictor of the class of a point than just any neighbor. A non-reciprocal neighbor is given in red here, which has a lower accuracy. So what do? We make a feature bank of all the features in the target domain, and we save their predictions. And next we make a affinity matrix A, in which we set to 1 all the reciprocal neighbors. And we have some hyperparameter R, which we use for the rest. So then the losses just try to minimize the difference between the probabilities of yourself and your reciprocal neighbors, just given here at the top. In top, you want to also stay similar to your own prediction. Is self-regulating. We use this diversity loss. We want to see all the classes seen in the training set. And finally, we went one step further. We say not only our direct neighbors, but also the neighbors of our neighbors have some knowledge about our state, which is this last expanded neighborhood. So this is tested on several domain adaptation methods. This is typical Office Home, is a typical data set, art, clip art, product, and real world images. And the Vista data set is another one, which is difficult. Synthetic and real images. And this is a 3D point cloud data. Yeah, so we do some ablation on the different losses we have introduced. So if you just use your standard method, you are, for example, on 62 on Office Home, and using these losses, we can get up to 72 accuracy, and you see that each of them contributes to a gain. The right corner. This is the self regularization, so that also gives a big jump. So comparing with state of the art, we managed to outperform shot, and mainly on Vista, you can see that it's in the corner, a reasonable jump for 3% improvement. What is also kind of interesting of this setting is that these top methods that all use the source data in the adaptation. But in this domain adaptation, you can see that actually the methods which do not use the source data are very competitive. I think if you update this data now, you can get the same results. But actually there is, in domain adaptation, it's really not that necessary to have the source data the model was trained on. There is little advantage to get from it, which was maybe a surprise for the group. And similar on this 3D data set, where we can get a significant jump from using the source model only. Okay, so this was let's say, a first idea how to adapt to a new domain which is unlabeled. So you start with a labeled domain, but now your second domain is unlabeled. We wanted to make one more step further, but now also care about the source domain performance. normally not the case in domain adaptation. And we call this generalized source-free domain adaptation. So this was the setting I discussed just before. So at test time, I only care about the target domain, but maybe I want, like in continual learning, I want to be good in all the domains at the end. And this is what we call generalized source-free domain adaptation. So no access to the source during the adaptation, and we aim for good performance on both domains. So in this table, we have now 3 classes, and only it still needs supervision in source domain. Here, let's say the base method is really this method I discussed at the beginning of the previous one, where we just push neighbors to have the same probability, which is given in the first part of this loss here, this log between the probability of the sample and its neighbors, S and K. We have the diversity loss, which is this KO term there. And if you just use this simple method, you can get the source model. This is just directly using your source model. For example, on Office Home, you get 84 versus 59. If you use this model, you do much better on the target domain. But what you see is that you will forget the source domain. So we needed to implement some continual learning strategy to prevent the forgetting of the source domain. And for that purpose, we use this attention masks. And while training on the source domain, we learn an attention mask, which picks out the neurons which are most relevant for the source domain. And it's very related with hard attention paper, continual learning. This is the mask definition. It's based on an embedding function E, and then given to a sigmoid. And in the end, it's really an almost binary mask. And what do we do with this mask? The important thing you do when you train the new domain, you use it to block the back propagated gradient. So parameters which are important for your source domain are not updated. So source domain performance keeps high. This drawback is that this is task aware. So at inference time, you have to say use this mask or use the source mask or the target mask. But if you use a small set of exemplars, you can make a classifier with as few as 100 we saw, which automatically chooses the. Now what we saw during training here in the top is that the performance on the source domain remains stable. It has still a drop in the beginning in the first iteration, but then it's stable. And that's what we want. We don't want this to continue following. So, and in the bottom, you see that if we now apply this sparse domain attention, now our source model accuracy jumps up to 81.8, which is much closer to the original source model accuracy. Here is the evaluation of the domain ID. And if you use, here you do task aware, so you know it. But if you use a classifier trained on 130 images, then you can get this result in this line. And you see that it's pretty close, so it works pretty well. And this method, obtained good results when compared with the state of the art at the time. We also extended this, so the normal is one source domain, one target domain, but you can do this for multiple target domain. So then all the target domains are unsupervised. So in this example here, we have 4 domains which we train, and only the first domain, AR, was labeled. And you can see that you can get good results, most results after training. But this is the performance after the 4 tasks in the last row, and it obtains good performance on all the previous tasks. So this is, let's say, one step of domain adaptation more in the direction of continual learning. We now care about both source and target performance. And we show that continual learning technique like mask attention can be used to get these results. Now I will shortly go in. This is work I did together with Bartolomé, so I think maybe you know it pretty well. So self-supervised continual learning. Self-supervised learning saw really an enormous improvement over the last years. by these contrastive learning methods, which use different data augmentations of the same patch and aim to map them to the same point in space. And for that, they use a view projector. And this view projector aims to map both the original image and the data augmented image to the same point in latent space. So, okay, in this case, we don't need any labels anymore. You can just compare what we would like. We extended two basic methods to this unsupervised or self-supervised learning frameworks, both LWF and EWC, which can be straightforwardly actually expanded to this setting. So one observation is what we made is that if you would just, let's say you have your old model here in gray, and you have your new model, which are training on your new task, and you just put what we call feature distillation loss on this, and you say, I want the features to be the same as my previous model. But this is very rigid. So this was observed in the botnet paper. This really hurts the plasticity. And botnet proposed different marginalizations of this feature space to solve this problem. And we have an alternative solution, which is a temporal projector, which we plug into between the backbone which is learned at task T and the previously learned backbone. And I think this is a very nice idea. And since then, we have used it actually in many projects, because this projector kind of allows you to learn new features in your new backbone. This projector will ignore the new features. It will map down all the features which it needs to find, get all the information of the previous backbone. And like that, it's hurts plasticity so it much less than this previous ways of addressing this. But it doesn't punish new knowledge. I think that's very nice of this sort of regularization. We have tested this on some settings, on Cypher 100 here. For example, okay, compared to the baseline. So we were the first to do that at that moment. Actually, there was another method called Castle at CVPR. At the same CVPR, this is at the workshop, which does something similar. It also works on, let's say, in self-supervised learning, you can evaluate on multiple downstream tasks. So here on cars and aircrafts. And again, it works nicely. I think this is interesting graph here. Maybe we look at the tiny ImageNet side where it's more clear. If you look at this, where you do look at forgetting and intransigence, and now you vary the parameter, which is the strength of your regularization. And what we want to be is in the left bottom corner, where we have little forgetting and we have high plasticity, which means low intransigence. And you see that this feature distillation really doesn't get into this corner. And with this PFR, you can get much better results. So low forgetting and high plasticity. One interesting example is where we really go to the many task setting in Cypher, where we take each class being one task. So first you train only on airplanes, then only on horses, etc. And this is it seems a very challenging setting, and it's still interestingly, it's still the red curve here manages to really extract quite some information. So quite amazing how these contrastive losses work, because all the images which you see at the same time are of the same class. So but even then it manages to learn a good representation, which is lower. Let's say green is, for example, the one you get with 50 tasks. It's lower, but still. So, okay, this is, let's say, the first exploration of continual learning in the self-supervised setting. And we show that some projection matrix can help to increase plasticity while keeping stability during training. I now want to go to the open world setting. So here at test time, you will see classes you haven't seen during the training time. So the standard setup is this one. Here you have a train set with some classes and the test set with the same classes. This is open world. So you have different classes in the test set which you haven't seen in the train set. The task of your algorithm is to say unknown. I don't know this class. Domain adaptation, as we saw, has this domain shift between the domains. And what we could call universal domain adaptation, maybe the most difficult setting is you have some classes in the train set which might not be in the test set. And you have some classes in the test set which are not in the train set. And you have on top a shift between the two domains. So there were some methods in this open world. Often what they do is they try to generate out of distribution data. So for example, this paper tries to generate out of distribution data by combining previous classes. So it takes a mobile or a calculator and a bike. And it makes this and it says that's an out of distribution class. And it used that kind of train the classifier and make room for these out of distribution classes. But okay, the drawback of that is that you really need to physically generate this out of distribution data. And we were wondering, would there not be, by student, another way to get the same effect? And he came up with a very simple idea, which works pretty nicely. And this is if you learn a normal cross-entropy classifier for two classes, for example, dog and cat at this moment. What he says, I introduce another class, which is out of distribution. And he didn't want to use any data, new data to train this other class. But what he does instead is he says the second most probable class of any training image should be out of distribution. So you say, in this case, it should first predict cat, and then the second highest probability should be out of distribution. Which kind of says for every class, its nearest class, the one which is next to it most, is out of distribution. Which in a sense you could kind of imagine if you think of infinite classes, there is always an out of distribution class which is closer than any of the other known classes. And so it's a very simple idea. It's very easy to train with this loss. And it works pretty nicely. Here is what happens during training. So here we have three classes. It's the black, red, and blue. The purple is out of distribution. It's not used during training. And a normal cross-entropy will learn a classifier like this one. It will just say, okay, this is my red class. Now I have a decision boundary here somewhere in the middle. I shouldn't have touched it. Yeah, one more time. Very crisp decision boundary. And what happens when you introduce this out of distribution class is that it actually makes space for classes you haven't seen yet. So this gray part is all out of distribution. And in this case, this pink class, which wasn't seen, actually drops in the middle. So the nice thing of this method is you don't need any out of distribution. You don't even generate to train it. And we tried it on a set of applications. This is the normal open set, so there is no domain adaptation problem. And it, let's say it got competitive results with state-of-the-art methods out there. Here now we have, this is called open set single domain generalization. Here you have some new classes in the target domain and a domain shift. And here you are not allowed to adapt to the target domain. And in this setting, so here in the bottom you see the drawing. No? So there's all the training classes are also in the test set, but there are new classes in the test set which you haven't seen. So here we obtained state-of-the-art results in this setting. SourceFree universal domain adaptation, the most difficult one. So some training classes are not in the test set and some classes in the test set haven't been seen. In this case, he added an additional loss for this domain adaptation and it also obtains excellent results. But this is currently at an archive. And this is on another data set, its own data set. So this is shows how to go beyond the closed world assumption into the open world assumption. So that brings me to the last part of the talk, in which will be on the multi-agent CL. And in our group, we have done a survey paper also with Bartolomé on class incremental learning. It got accepted this year, and there is code available online. And one of the graphs we had in this method, I think maybe the most, I would choose one standard experiment. It's the Cypher 1010, where you learn Cypher 100 10 tasks. And if you look at the results, then the winner is the global distillation method. And what is this global distillation method doing? It's using let's say in some sense, multi-agent approach. It has a specialized expert, which only focuses on learning the new task. And then it has a second step. That's the first step. The second step, it distills the information of the previous network, which has all the knowledge, together with this new expert together. And in this paper, they propose to use external data to do this distillation. But they also, in this comparison, we only use data from the exemplars, and it also works pretty well. So it was the best method in the comparison. So we worked on some ideas in this direction. So the nice thing of this expert is that it can really focus on learning the new knowledge of the new domain without having to not forget. So here in this case also, let's say you have an old model, then you just have an expert which specializes on the new data, maybe still some regularization, but light. And then there is some fusion, and you want to be good on all the time. So one work which now presented this week at CVPR is where we relook at weight averaging, where instead of, let's say, the drawback of the GD method is that you really have to distill these two methods into a single method network again. So you have another sort of a pause, you have to distill it with some data. Instead, we just look at weight averaging. So you just take the two networks, you average the weights, something which is very often used in federated learning. And it's not used in continual learning a lot, because the assumption was that the networks are too far away. And instead of just averaging, we have here a parameter alpha, weights the two, the old model and the new model. We propose a simple equation to dynamically change this alpha during training based on how many old classes there are versus new classes. And here in the ablation, you see that if you use this, this dynamic alpha, you get better results than any of the fixed alphas, so it kind of works. And this is all evaluated for incremental semantic segmentation. And you can plug it into some of the existing methods. So MIB is maybe the most known incremental semantic segmentation method. And you see it can really get immense, super increase in performance. So it jumps from 32 to 65 in this method by just doing something as simple as averaging the weights of an expert network and the previous network. So I think this is an interesting idea, this weight averaging, which maybe we have to also revisit in maybe image classification or image classification-based continual learning again. Here we only did it in incremental semantic segmentation. Here is some results. So in incremental semantic segmentation, it's a little bit a particular setup where at every task you only get the labels of one class normally, or several classes, but you don't get the labels of all the previous classes anymore. But these classes are present. So for example, here in the base classes, I think human and dog was already present. But then later you learn about sheep. And you see that if you go on through the whole line of classes, in the end here, let's say the standard method was having some problems with mixing up sofa with sheep, whereas the adaptation works better. One other paper we have now on archive in this, let's say, multi-agent continual learning setting is this one where we have what we call self-centered devices. It's more sort of an edge computation setting. You have a main model which you employ in a self-centered device which just wants to be good in what it aims to do. So it doesn't want to sacrifice any of its energy to prevent forgetting. And it also doesn't want to share the data. So you communicate this model back to your main, let's say maybe the cloud. And there you want to consolidate your old model and the new models which are coming in sequentially. Did I say here? Oh, yeah, okay. So so in the model fusion, what I write is not totally correct, but the data which is used on the device is not available. You could use other data. Very quickly, what we did here is we use an expert. So this expert is here on the bottom. Again, it can learn with its task as good as it wants. And then now in the fusion phase, we use KD losses between the expert here in the bottom, the previous model in the top, and the new model which is on the right. And we introduce one extra model, which is related to the one we used in self-supervised learning, which is projected latent distillation, where we project the latent spaces of these two, the previous model and the expert, to a new space. So we want this new model to have the knowledge of both these networks. One interesting thing in this, I don't know if who in this room has seen this image?
Just noticed that.
So this, wait, I have it here. This is work of Sano. It's really very, it's now also now at iClear, maybe it was something previously, but he shows that you can do this, train a network on a single image. So he trains a neural network on this image, and he does a lot of data augmentation, and he gets amazing results on it. So shows that for even for action recognition and even for audio, he does something. So motivated by that, we thought, okay, let's try to do this whole distillation phase in our network here, where we have this expert model coming in on only a single image. Will this work? So we evaluated also in this paper. This is the ablation of this double latent space projection layer loss. And it gives a decent movement here, for example, the tiny ImageNet of 8%. And then on the right, maybe more interesting is this results what you get if you do a distillation on a single image. So you could use the current data, which is what we normally do. Continual learning, you get 84. If you use the whole of ImageNet, you get a little bit better. And then there is a number of single images below this, which is used. And you see that if you use the city image, what we used, you get 80.5. Actually, animals image is doing a little bit better than this. But it's amazing how good you can do distillation of different networks based on a single image. So that brings me till the end of my talk. I talked about more label efficient continual learning. We are now looking into maybe more semi-supervised settings where only some data on the stream is labeled. And we are thinking about extending theory also for active learning. So maybe you actively ask labelers for some labels in the stream. Here we want to move also to class discovery. So can we really, instead of just saying all these classes are unknown, can we cluster these unknown classes already into separate classes in a continual learning setting? And here, okay, we are interested to go beyond 2 agents. And I think especially this weight averaging is very easy to apply also to multiple. 2 other things I will work with on at the moment. This is continual learning and interpretable algorithms. This is together with the GMUM group in Krakow. And now also here with IDEAS, we're working on early exit to combine early exit and continual learning. I'm also very enthusiastic about these projects. Okay, that brings me to the end of the talk. Thank you for your attention.
Thank you very much. And yeah, questions?
So this fusion of endpoint fusion for when you merge different networks, I think usually you assume that those are like pre-trained models, then it's easier to merge them. So was there any trick to whether, because I assume that those were not pre-trained models?
Yeah, we did. In the end, we did use a distillation loss here between, so it's not a totally free expert. If we did see that if you let it totally free,
okay,
it could end up with weights which are not solvable anymore. But in principle, it's I think it's trained from scratch.
Yeah, but then there's distillation loss. So
yeah, because here, for example, that's also why in MIB it's a sort of a fancy distillation loss, especially designed for this incremental learning setting. But there you also apply MIB algorithm, and at the end, you just sum it with the previous model. Average.
So one question about the incremental semantics, like does it work that in different tasks you see the same images but more labels, or those are also different images? The images are different, or
I'm not totally sure there. Yeah,
because if they would be the same, then it might be also easier for.
Yeah, in a sense, it's easier because you know you get at least some replay for free. No, you have you see previous classes also in the, but you do have to explicitly handle this problem, because if you just say this is background, then you start making errors. So that, let's say that problem is solved by IMIB example. In incremental object detection, it's the same setting.
Okay, thanks.
Any other questions? So just to pause then for a question. So I like the motivational sustainability. But is there any, or any like real evidence, methods actually other approaches on top of just this philosophical thing needs? But have you seen any works on like this energy topic on top of hope? Or is it something that we just throw around as a hope that nobody asks?
Let's say this fundamental problem of this warm starting paper, they show that it's they can reduce training by 50%. They show clocks or the number of epochs, But there, maybe there is some evidence there. Yeah, okay, it would be nice to be able to get down to 10%, or something to really. Let's say the fact that there are no results yet, I do think it means there are no easy. It will not be easy. Yeah. I've done quite some work in active learning, which was where you have all your unlabeled data and you have to say what are the samples which are most relevant to be labeled for my learner. And it's also a very difficult field. And I think it's related with this sustainable continual learning in the sense that the question, what of my previous data I need to replay, it's very related. I think the functions which are developed in this active learning community can be applied on this field as well. But in active learning, the gains are also, it's hard to get super high gains. Random labeling works pretty good.
We don't work
Yeah.
Okay. Any other questions, or maybe from the poll? Last comments.
Maybe it's not related to, but how can you train a network on a single image? What are the, how do they do this?
Like full HD on
Yeah, it is. So I think it's a bit with this contrastive learning. No, they moved a lot this data augmentations, different data augmentations, map it to the same. And here it's a bigger image. It's not a small image, but and then they do really all the data augmentation. Yeah. But okay, it just by and but I think it's like contrastive learning. So you want to map it to the same point again. Yeah, in distillation it's easier what we did. You don't have to.
For the single image, I think it's like the table is like 10% of the T4 data set size. It's one image, but it's pretty large compared to the small T4.
Yeah, but he also trains compares to ImageNet.
It's a good image.
Yeah.
All right. I guess that's it. So thank you again for coming over. It's really great. And let's continue over the projects. I think we have quite a bunch of projects that potentially could be. Thank you again. And